Another theorem that we have to use to prove that two triangles are congruent is something called the side angle side, or in short SAS Congruence Theorem. And this says that if two sides and the included angle of one triangle are congruent to two sides and included angle of another triangle, then the two triangles are congruent. So the key word here is that that angle has to be included. So you'll notice over here that I have two pairs of congruent sides, and it's the angle that is between those two congruent sides that are congruent. So this wouldn't work if, for instance, it was actually the angle over here, because that would not be the included angle. It has to be the angle that is between the two congruent sides. So we'll see here in my example that because I have two pairs of congruent sides and the angle that is formed between those congruent sides is congruent, these two triangles are congruent. So I'd have triangle ABC is congruent to, so I see for A to B, that is the side that only has one tick mark. So the side that only has one tick mark here is D to E. And I have to do that in that order because E is congruent to angle B, so they both need to be that second letter. And so I get that congruency statement. Okay, now let's try some proofs with this. So for number one, I'm given that BC is congruent to DA. So I have that tick mark here. And I'm also given that BC is parallel to AD. So again, I always start with my given information. And in my given information, I'm already given a congruent side. So I have that here. So now I just need to find another side that is congruent and then an angle. So I'm going to first use my given information. I'm given that BC is parallel to AD. And so if you remember from our previous unit, when we have parallel lines, we have some congruent angles that are formed from that. And so to kind of look at that, you can extend this out so that it looks more like our parallel lines cut by transversal. And we can see some of the congruent angles that we get from here. And looking at this, I see that I have alternate interior angles that are inside here. And if you remember, alternate interior angles are congruent. And so I can then say that BCA is congruent to angle DAC. So I have angle BCA is congruent to angle DAC. That's by the alternate interior angles theorem. So I have an angle, I have a side, now I need to get another side, and the other side needs to be on the other side of my congruent angle. So that's going to be this side AC. And we know that's congruent because the side is always going to be congruent to itself. So I have my third side, and that's going to be my reflexive property. And so I have a side, an angle, a side, and it's in that order. So that means that triangle ABC is congruent to triangle CDA. That's made by side, angle, side. Okay, let's try another one. Here I'm given that L is the midpoint of KN and L is also the midpoint of JM. And I want to prove that triangle JKL is congruent to triangle MNL. So I see that L is the midpoint of basically both of these segments, and so if you recall, for midpoint, that means it's going exactly in the middle, and so it's cutting it in half. So since it's a midpoint of Kn, that means that KL is congruent to Ln. I'm actually going to write this all in one line. So KL is congruent to Ln. And we have that JL is congruent to LM. And that is definition of midpoint. So I have two sides here on this line that are congruent. Now I need to somehow justify that this angle that is formed between them is congruent. Well, looking at this picture, I see that those two angles are vertical angles. And we learned in one of our previous units that vertical angles are congruent. So I can then state that angle KLJ is congruent to angle MLN. And that's by the vertical angles congruence theorem. And so now we see that we got our needed angle. So I have a side, angle, sides. Now I can therefore state that these two triangles are congruent. And that's by the side, angle, side theorem. Okay, let's look at one more. So here I'm given that QP bisects angle RQS and QR is congruent to QS. So I have a congruent side already to start off with. Now I need to remember what it means that QP bisects an angle. QP bisecting the angle means it's cutting that angle in half. So it's creating two congruent angles. So it's bisecting RQS here. So that means that these two angles are congruent. So I have that angle RQP is congruent to angle SQP. And that's just going to be definition of angle bisector. So I have an angle. Now I just need another side. And remember, the order here is super important. That congruent angle needs to be between the two congruent sides. So that means this QP needs to be congruent. And just like we saw in a lot of these other examples, and usually for a lot of these proofs, this may end up showing up a lot. So definitely a good thing to watch out for. I see that QP is congruent to itself. And again, that's by my reflexive property. So I have a side, angle, side, and it's in the correct order with the angle between the two congruent sides. And so now I can say that triangle RQP is congruent to triangle SQP. That's by side, angle, side.